Welcome to the second day of Riemann Sums, AP Calc students. We are going to approximate integrals again using left and right Riemann sums, except now our data is represented in a table form. So we're approximating the area under the curve of this function, but we don't know what the function is. We only know 5 data points on the function. So I've included an XY chart, a grid. So if you want to be visual with it, you can. So I'm going to do that quickly. I'm going to pause the video and just graph these points quickly. Okay, so I plotted the points. This is all we know about this function. I actually have no idea what the function's doing in between these points, but I do know that overall it's increasing just in general, but we really only know these points. So if you want, you can sort of connect the dots if you want. Like technically we don't know what it looks like, but I'll just connect the dots here in yellow. That's just one possibility for what f of x could look like, right? Another possibility is that it might dip down in between the points, whatever. We only know the orange, and the yellow is just my prediction for what the function looks like. Okay, so let's approximate using a left Riemann sum. So the left Riemann sum we'll do in blue here. And we can see that there's 1, 2, 3, 4 intervals, right? The interval between 0 and 2, 2 and 5, 5 and 7, and 7 and 10. So we can only have 4 rectangles here. Even though there's 5 data points, that will give us 4 rectangles, right? So if you want to be visual about it, our first left Riemann sum will look like that. Our second will look like that. I didn't quite go far enough there. There we go. Our third will look like that. And then our fourth. Not the best looking rectangles, but you get the idea. Okay, we can see that these rectangles, unlike yesterday, don't have equal base lengths, right? Like the base length of our first rectangle is 2 units. That's because the distance between those x values is 2. Whereas the delta x here, our base length, is 3 because the distance between 2 and 5 is 3. This one's a gap of 2. This delta x is 3 here. So we have different values for our base times our height. So we don't have a consistent base anymore. The heights are still found using our f of x, right? But if we look, since we're using a left Riemann sum, our first height is the leftmost f of x value, which is 2. Our second height is 3. Our third height is 5. And our last height is 7. We actually don't ever use this rightmost height of 8 for the left Riemann sum. We only use the ones to the left, starting at the left. So finding it now is just doing base times height. So our first rectangle, the base is 2, and the height is found here, which is 2. Okay, our second rectangle, the base is 3, the delta x, so the distance between these two x values is 3, and the height, so if you look at these two, you go to the left to find the height, which is 3. Okay, our third rectangle has a base length of 2, which we can find here. The gap between 5 and 7 is 2, and it has a height of 5. And our last one, our base length is 3, that's our delta x. And then we go to the left height, which is 7. Okay, so we end up getting 44. I hope my math is right there. Just did it real quick. So we didn't know, it looks like based on the yellow sketch that I did, which is just a guess on my part. It looks like this is an underestimate. If we were told that f of x was increasing for all x, we could definitely say that this was an underestimate because it's the left Riemann sum and the function's going up, it's increasing. So if we assume that the function was increasing for all x, or if we were told that, we could, definitely say that this value is an underestimate. Okay, let's look at our right Riemann sum. I'm going to write this out in a slightly different way, just to show you different ways that you can be tested on the exam. Okay, our right rectangles are going to go from the height to the right. So that's our first rectangle. This is our second one. This is our third. And that's our last, the fourth one. So we're going to basically be doing the same thing, but just with one different height. Okay, so our first rectangle, I'm still going to go from left to right here. So this first rectangle, it has a base length of 2, again because the gap between these two x values is 2. But then we're using the rightmost height, because if you see, this height is now 3 because we're coming from the right. So one way that the AP exam could write this is that instead of you just doing 2 minus 0 in your head to get that this length is 2, it might write it out like this. So that's like the base. And then multiply by the height, which is 3. So this is just an alternate way of writing the area of this rectangle right here. They got the base by doing 2 minus 0, because the base is the difference between your x values, and then the height is 3. Let's practice writing that in this alternate method for the next rectangle. So for this next rectangle, the way that we find this distance, other than just looking at it and seeing that it's 3, is you can technically do 5 minus 2, right, to get this length of 3. So that is our base length. And then what's our height? Our height is up here at 5. So we saw that, okay, it's the gap between 2 and 5, and then we went with the rightmost height of 5. Okay, you try the next two. I'm going to pause, and then you can play and check your work. All right, we had a right Riemann sum of 59. And again, if this function was increasing for all x, or at least from 0 to 10 if it was increasing, then we could confidently say that the right Riemann sum was an overestimate, because since our function's increasing, the rectangles formed from the right height, the height from the right side, is greater than the area under the curve. Cool. All right, that's how you do a Riemann sum with a table. Note that sometimes you're not going to be told exactly how many intervals to use. It doesn't say use 4 intervals. Basically, unless you're told otherwise, you're basically just going to use all the data that you can. So since we had 5 data points, we could use 4 intervals. And again, I just drew this out because it helped to teach it in a visual way. You don't need it, right? So you could theoretically just get all this math over here just from the table. You don't necessarily need the visual, but if you like it, then I recommend that you draw it out just to help you. Okay, this next example delves under the x-axis a little bit, and we haven't really discussed this yet. So I'm just going to, so again, all we know are these 6 data points. We don't know what the function looks like in between the data points, but I once more am going to make my best judgment in yellow. Something like that, that's fine. So as you can see here, we have area underneath the curve, underneath the x-axis, and then we have area above the x-axis from 0 to 19. And what that means is, even though area technically can't be negative, in calculus, this value, this area that's underneath the x-axis is considered a negative value, and the area above it is positive, and then our final integral is the net. It's like profit, right? You take how much money that you actually brought in, but then you have to subtract all the money that you spent on your supplies and stuff. So your profit is your net money. It's how much you have left over after subtracting all the stuff you spent on your supplies. It's the same idea here. This wouldn't be a very good net, but because we have a lot bigger of an area under the curve than we do above the curve, our integral value that we get is going to be negative, most likely. And that's because, again, this negative portion is much larger of a value than the positive portion. So, again, we didn't need to necessarily draw it to see that. However, it might help us visualize a little bit kind of what we're doing. All right, let's go ahead and do our left and right Riemann sums. I'm going to do this one entirely without drawing the rectangles and show you that you'll still get the answer just using the table. So let's erase on the table, and let's just use the table so you guys can see an example just using the table values. All right, we can see we have 6 data points, so we're going to have 5 rectangles. Oops, almost wrote 4. Okay, so our left Riemann sum will be in blue here. So we want to look at the distance, our delta x, right? The distance between 0 and 4, okay? Again, I keep saying delta x, delta just as a triangle. It just means the distance in between or the difference. And so our delta x here is 4. That's our base length of that first rectangle. And then we want to use the height from the left. So we're going to use a height of -3, and that's our first rectangle. Our second rectangle is going to use the next delta x. This delta x here is 5, 9 minus 4. So that's the base length of that rectangle. Then we're going to use the left height, which is -5. I'll do one more and then let you guys practice the next two. This next delta x here is only 1, 10 minus 9, and then the left height of 4. Go ahead and try the next two and then get your final answer. Okay, so we end up getting our left Riemann sum to equal -52. Let's move on to the right Riemann sum. Okay, our right Riemann sum, again, we have 5 values that we add together. And so our right Riemann sum, I'm still going to start from the left side here and still do my delta x, but then I'm going to use the height that's given by the rightmost x value in that rectangle, which is the height provided when x is 4. So in this case, our delta x, our base length is 4, 4 minus 0. That's our base. Our height is -5. How can a height be negative? Well, if you were to draw this rectangle, there it is. So it's really only because this rectangle is below the x-axis. That's why. Okay, our next one, our delta x, our base length is 5 again. Or sorry, is 5, just and then the height is -4. Okay, go ahead and try the next couple. Pause the video and then play to check your work. All right, we find that our right Riemann sum is -37. So make sure you check your work. And let's move on to an example that just looks a little weirder, but is the exact same idea. All right. This is one that is AP-esque. I made it up, as you can tell, by my handwriting in that beautiful table there. But this is one that's like, do you know what you're doing in a more conceptual way, right? Rather than just plugging and chugging like we've kind of been doing. Basically, that's half the AP test anyway. So it's the same idea, except we can't necessarily get values for delta x here that are numerical, right? So the reason in the first example I had us write our base of our rectangle length as 4 minus 2 or something instead of just 2 is because sometimes in a more conceptual problem, that's what we're going to have to do. So let's write the expression for our left Riemann sum. It tells us to use 4 subintervals, which we already knew, right? Because we have 5 data points, we're going to have 4 separate intervals. And again, we just want to approximate the area under the curve h of t, which we don't know really anything about, right? But I did mean to write one more thing on here, so let's include that. I should have included that h of t is decreasing. That's a point I wanted to make, and I just forgot to write it in there. So let's include that h of t is decreasing. We can sort of see that with the y values here, but we want to make sure that it's totally decreasing everywhere and not just at these random 5 values that we've picked. Okay, let's write our left Riemann sum. So L. All right, so our left Riemann sum needs to do base times heights again. And in order to find the base, remember it's the delta x. And in this case, it's delta t, just because t instead of x is being used here. Who cares? Same idea. So we can't really do this and just get a number, right? So we're just going to write it as a minus 0. That's it. Then we want to use the height provided by the left t value. So the height provided by 0 is 6. So that's our first rectangle. That's our first rectangle. Our second rectangle would be, again, the base length of that rectangle, delta t, the length between a and a squared, which we write as a squared minus a. And you can't simplify that at all. Multiplied by the height given by the left t value, 4. Okay, let's try our next one. Plus 3a minus a squared. And then the height provided by the left, 3. And then you go ahead and come up with the last one. Okay, there's our last one. That's the only one that I could simplify because you can actually do 7a minus 3a. The only ones that have like terms, right? So again, this might not be even written as a minus 0. It might be just written as a. This potentially could be written as 7a minus 3a. You know, just different ways of showing things. I simplified it. Who knows? They might not even show this one because it's times 0 anyway, so it goes away. But either way, this is just an alternate way of writing an expression. The reason that I talked about this being a decreasing function is if we were to plot something that was decreasing, oh, there we go. So if we were to plot something that was decreasing, h of t, and right, just some random function that was decreasing, sure, that could be h of t, and we were to do the left Riemann sums. Well, if I were to draw rectangles from the left here at any points, however many that I were to draw, take a look at how those left rectangles, even if I started there, look at those left rectangles. They are overestimating. What I'm coloring in blue is the estimate of the area under the curve. So because h of t is decreasing, the actual area under the curve is just in orange, the area under the function. And those blue rectangles are not only capturing that entire area, but even more than that. So, because a function's decreasing, the left Riemann sum approximation would end up being an overestimate because h of t is decreasing. Now, I guess there's rules to this, right? Depending on if something's increasing or decreasing, the left or right Riemann sum would either be an over or under approximate. I personally just like to sketch it out and look, or just think about it in my head. Again, I'm pretty visual. So it seems to help. If you draw something going down and you make rectangles from the left, they're going to be bigger. So it's an overestimate. It really is that simple if you just want to sketch it out. So again, this is one where we couldn't actually get a numerical answer because we weren't given all numerical values, but it's the same idea. I included this one not because it's part of your assignment today, but because you'll see it on AP Online for your assignment tomorrow. Okay, this is your assignment for today. It will be due tomorrow by noon on the Dropbox. The first one is basically like the first two examples that we did. Approximating using both a left and right Riemann sum. No, you don't have to sketch it if you don't want to. I'm not looking for that here. And you can just use the table to help you. Again, I'd recommend writing this all down on your paper so you have a nice extra example problem to look at instead of just writing the answer on your paper. For number 2, this one does have you sketch something. It's a little bit more conceptual. So this shouldn't take you too long. Best of luck, and I'll talk to you guys soon.